Para dar inicio a la ceremonia les pedimos que mantengan sus micrófonos apagados, por favor. Muchas gracias. Muy buenas tardes, estimado rector, decanos, profesores, distinguidos invitados. En nombre de la Universidad Adolfo Ibáñez y de la Facultad de Ingeniería y Ciencias, le damos la más cordial bienvenida a todos quienes nos acompañan en esta ceremonia de lanzamiento del Doctorado en Data Science de la Universidad Adolfo Ibáñez. Para dar inicio a esta ceremonia, se dirigirá a ustedes el rector de la universidad, don Harald Beyer Burgos.
Buenas tardes, muchas gracias por acompañarnos. Es un gusto tenerlos presentes en esta pequeña ceremonia con la que anunciamos oficialmente el doctorado en ciencia de datos. Saludo al decano, al director del doctorado, a los académicos y a todas las personas que nos acompañan hoy día. Hace pocos días leía un artículo, más que un artículo, un libro sobre historia de Egipto, y había un capítulo bien interesante sobre lo que yo creo era ciencia de datos, digamos. Y básicamente contaba el capítulo sobre cómo los egipcios acumulaban durante muchos años datos para predecir inundaciones por el caudal que traía el Nilo, y era un algoritmo bastante sofisticado para la época que intentaba de alguna forma a través de estos datos construir un algoritmo que les permitía saber exactamente cuándo el Nilo se iba a desbordar y las consecuencias que iba a tener. Ciertamente eso yo creo que era un ejemplo muy rudimentario de lo que era ciencia de datos. Y desde ese entonces, digamos, han pasado cientos e incluso miles de años, y creo que hoy día nos encontramos frente a un fenómeno realmente extraordinario, y que es esta cantidad de información y de datos que se están acumulando en el mundo en distintos ámbitos y que nos permiten de alguna forma entender mejor fenómenos físicos, biológicos, sociales, económicos, y que indudablemente requiere de capital humano avanzado para lidiar adecuadamente con ellos y producir a partir de esos datos, ¿no es cierto?, algoritmos, y más que algoritmos, comprensiones interesantes de los fenómenos que nos acompañan como humanidad. Este doctorado precisamente lo que aspira es a desarrollar ese capital humano avanzado para generar profesionales que no solamente en Chile, sino que en toda América Latina probablemente puedan a través de esta preparación usar satisfactoriamente estos datos que se van acumulando y hacer un aporte a la generación de conocimiento, y en algunos casos también a la aplicación o a la resolución de problemas complejos que las sociedades en las que vivimos están teniendo y que se pueden iluminar de alguna manera, ¿no es cierto?, a través del uso de métodos científicos que trabajen estos datos de manera mucho más efectiva que lo que ha sido hasta ahora. En ese sentido, para la Universidad Adolfo Ibáñez es realmente un gusto tener la oportunidad de ofrecer este programa, y esa posibilidad se genera porque tenemos un grupo destacado de académicos que ha ido desarrollando una experiencia, una expertise, un conocimiento, y se ha ido preparando para poder ofrecer un programa de alto nivel. Creo que este programa, cuando uno lo mira en detalle, se da cuenta de las bondades que tiene, de la calidad de su cuerpo académico, del conocimiento que está generando ese cuerpo académico, y debería ser un programa extraordinariamente atractivo para profesionales no solo de América Latina, sino que yo me atrevería a decir de otros lugares del mundo, porque se compara, creo que favorablemente, con programas de esta naturaleza que existen en universidades europeas, en universidades asiáticas y en universidades estadounidenses. En ese sentido, como rector, yo estoy muy orgulloso de que podamos ofrecer este doctorado, que podamos dar este aporte, porque las universidades finalmente tienen que estar empujando programas atractivos, tienen que estar formando el capital humano que las sociedades modernas necesitan, y al mismo tiempo incorporando jóvenes o no tan jóvenes que quieran de alguna forma beneficiarse de esta acumulación de conocimiento que la universidad va desarrollando a través de sus académicos, a través de sus redes, a través de sus prácticas. Y este doctorado creo que es un buen ejemplo de cómo una universidad privada, que es una pequeña, que se acaba de acreditar en la categoría de excelencia, puede contribuir a seguir engrandeciendo el patrimonio cognitivo del país, engrandeciendo el capital humano del país y de la región, me atrevería a decir, y también como una universidad puede de alguna forma asegurar a los profesionales que se interesen en este doctorado oportunidades de crecimiento personal extraordinariamente valiosas. Y en ese sentido, creo yo, como universidad estamos cumpliendo con dos funciones sociales que son esenciales de todo proyecto universitario. Por una parte, ¿no es cierto?, formar profesionales preparados para desafíos complejos, y por otra, generar avances en el conocimiento que indudablemente las sociedades modernas requieren con urgencia. Muchas gracias y felicito la iniciativa de la Facultad de Ingeniería y Ciencia, de su decano y del director y el cuerpo académico de este programa de doctorado. Muchas gracias.
Agradecemos las palabras del rector. A continuación, dejo con ustedes al decano de la Facultad de Ingeniería y Ciencias, don Carlos Jerez.
Muchas gracias, Natalia. Muchas gracias, señor rector, por participar de este evento. Muchas gracias a las autoridades académicas que también nos acompañan, a nuestros propios académicos, tanto de la UAI como de la Facultad de Ingeniería y Ciencias, y a todos quienes hoy participan de este hito, sobre todo al profesor Leopoldo Bertozzi, quien ha impulsado esta iniciativa. No me voy a alargar mucho en el rol que hoy los datos tienen en el desarrollo no solamente de nuestra economía, de la sociedad, del impacto que su uso y mal uso pueden generar en nuestras vidas, el uso también que se le está dando en contextos completamente inesperados, que van desde la arqueología, tomando un poco lo que comentaba el rector en torno a Egipto, también lo vemos en música, sociedad, derecho, en fin, un sinnúmero de aplicaciones, y sin duda alguna que uno podría decir que vivimos en el mundo de los datos y que esto solamente va a seguir creciendo. Los datos no como el nuevo petróleo, porque no son un bien escaso, al contrario, a medida que van generándose más y más datos y mayor uso de los mismos, más valor estos tienen. Por lo tanto, las lógicas aquí son bastante interesantes desde esa perspectiva. Pero la ciencia de datos se ha transformado en un habilitador de diálogos interdisciplinarios. Y diálogos interdisciplinarios que son particularmente relevantes en un contexto de un mundo más complejo, donde el cambio climático, entre muchas otras dificultades sociales que vemos, económicas, y la complejidad de las mismas, lo único que han hecho es evidenciar la necesidad de contar con mejores y más robustas técnicas para procesar, analizar, anticipar escenarios. Y es en esa lógica que entonces la Facultad de Ingeniería y Ciencia, a través de su plan estratégico al 2030, Smart Plus Sustainable, ha considerado que la ciencia de datos tiene que ser algo fundamental en la formación de cualquiera de nuestros alumnos, sea de pregrado, sea de posgrado, sea independiente de la especialidad que sigan. La ciencia de datos se transforma de alguna manera en una de las herramientas que necesitarán cada vez más para poder cumplir con sus roles de manera eficaz. Y es en esa lógica que la facultad y la universidad han decidido tomar un camino para ser protagonistas en Chile y en Latinoamérica, y ojalá a nivel mundial, de el desarrollo de estas técnicas, de desarrollo de este conocimiento y de su aplicación a distintas áreas. Y es en ese sentido que vemos que la inversión y la creación de programas por parte de la UAI a través de nuestra facultad ha sido impulsada de manera muy enfática, con mucha energía, y este doctorado se suma ya a la creación de un magíster profesional para ciencia de datos, magíster en ciencias para ciencia de datos de carácter académico, la incorporación de ciencia de datos en varios de los programas también, como el magíster en ingeniería industrial y administración de operaciones, el doctorado en sistemas complejos también ya ha ido adoptando elementos de acá, y esperamos próximamente tener también una licenciatura. Entonces este doctorado es en cierta manera una evolución natural de esta lógica de posicionamiento de todo un ciclo de formación de capital humano avanzado, como parte también importante de un ecosistema en ciencia de datos, pero que a su vez tiene spillovers o tiene impacto sobre muchas otras áreas, también con los mismos centros de la facultad, que ya vemos programas conjuntos con energía y otras áreas que tienen que ver con temas satelitales, los de datos satelitales, una conexión internacional que hemos estado impulsando también desde el año pasado, cada vez más fuerte, y que queremos ver que estos alumnos y nuestros investigadores de este programa sean capaces de ir incorporando. Y una iniciativa a nivel nacional de la cual la UAI es socia fundadora, que es el Data Observatory, cuya misión es justamente procesar, almacenar, disponibilizar grandes cantidades de datos que tengan impacto global, y por lo tanto también vemos como un elemento clave en esa construcción la creación de este doctorado para poder aún más profundizar en las necesidades futuras tanto de la creación de conocimientos como la aplicación de los mismos. Así que con esto solamente agradecer una vez más al equipo de académicos que estuvo junto al profesor Bertozzi desarrollando esta iniciativa, agradecer también a la universidad que nos haya dado el apoyo para esta, y desear que este sea un programa muy exitoso hacia adelante. Así que muchas gracias.
Muchas gracias, Carlos, por tus palabras. Continuando con el programa, se dirigirá a ustedes el director del nuevo doctorado en Data Science, el profesor Leopoldo Bertozzi. Profesor Bertozzi hará su presentación en inglés por la presencia de nuestro invitado internacional, quien será introducido por él al término de sus palabras.
Okay. Good afternoon, everyone. Can you see my slides, right? Okay. Well, I'm going to tell you about our PhD program in data science, some relevant aspects of it. And then after a few slides I will present, we will continue with our international invited speaker that I will introduce. Okay. What does this PhD program mean for us? I mean, it's a unique opportunity, a challenge, and a responsibility. Yeah, data and data science, they are here to stay. They are omnipresent in our life and in our activities. They are far from being a fashion, and so and the relevance of data science can only increase. And we understand that data science in a broad sense, considering different disciplines that are part of it or are relevant in this new area of data science. I mean, we find data management that goes much beyond traditional databases. We find applications in business intelligence and artificial intelligence. Many areas of artificial intelligence are relevant for data science. Most prominently, perhaps, is machine learning and natural language processing, knowledge representation or reasoning, ontologies, and knowledge graphs. There are many applications of knowledge graphs in these days, and so this is a really hot area of research and applications as well. We are Also, I mean, including in data science, everything that has to do with uncertainty management and representations of uncertainty or uncertain knowledge, statistical methods in data science and machine learning, and of course, plenty of application domains where data science has an important role to play. And data science, in this broad sense, again, I mean, it's under constant evolution. That is very important to have in mind. There are always, every day, important new problems and areas that are emerging, and research areas that are become relevant. Without trying to be exhaustive in this regard, I mean, I'm going to mention a few of them. In the last few years, I mean, there has been a lot of research, active research, on explainability, fairness, bias, transparent and ethical AI and data science. Also, machine learning, data management, business intelligence in the cloud. And it's also becoming crucially relevant in these days. Also, database, machine learning in database. I mean, traditionally, people have used the database to store data, then they move the data somewhere else outside the database, they do machine learning. But the idea is to try to take advantage of the existing and improved technology around databases to do machine learning inside the database, and in that way, optimizing all the underlying processes. This is also a very promising area of research. Now we hear a lot about quantum machine learning in relation to the broader area of quantum computing. It is also gaining prominence. People have realized that, in particular, artificial intelligence and data science, they are not going to go too far if we don't take into account, I mean, new disciplines or older disciplines that have something to say important about them. That I mentioned here, neuroscience and cognitive science are playing an important role as well. And also neurosymbolic approaches to AI. That is what our invited speaker is going to tell us about. This is very important because now the idea is to try to combine different techniques, different schools of AI and data science to produce really intelligent systems and agents, right? So we need a combination of approaches, and well, this is a very important new areas that are emerging every day, and our university is confronting all these opportunities. It is a major effort for a fully private university who has to take that into account. Yeah? It's not an easy task, but I think we are up to the challenge that this means. And so, in terms of what we have been doing so far, well, the university and our faculty of engineering and sciences have been building, and still are building, a solid data science group, among the largest in the country. It is unique in some sense, in the sense that it brings together researchers from different areas, different disciplines: computer science, statistics, mathematics, engineering, and application domains. This is very important, I mean, in data science to produce this multidisciplinary approach and view of things. The PhD program is building upon the successful experience of our Master of Science in Data Science. We started with it 2 years ago and counts today with around 40 students. It is a 2-year research-oriented master's program. So this experience has been extremely useful to think of a PhD program. It is our contribution or response to the data science related challenges and opportunities that emerge. And we expect to make a contribution in the sense that our country needs more and better trained data scientists, and we hope to help in that regard. We have perceived both a widespread need for an interest in a data science related PhD program. And we have dreams, we have aspirations, we aspire to become highly relevant in Latin America. We expect to attract the students and researchers from the whole region. And we have our goals and our dreams. I would like to mention some of them that are really important, and they guide us in this adventure. So we want to be recognized by the international community for the quality of our research and our graduates. We want to produce high impact research and also publish publish highly cited research paper. That is an important goal. We want to be present in every regard at the venues where the relevant researchers publish and gather. They are the truly important international conferences in the world. And in this sense, I think I cannot resist but mentioning that this important conference on general, they seldom coincide with those that are our national funding and accreditation agencies mistakenly considered to be relevant in data science and computer science. This amounts to sending the wrong signals and setting the wrong incentives and forcing us to make a double effort. The problem is that Chile, in relative terms, is publishing a lot. However, the impact of the research is, again, in relative terms, is low. So we have to improve on that, and we have to take care of this important issue. The PhD program is intended to be completed in 4 years. Of course, as every PhD program, this is the plan. I mean, things can happen in a different way, as you know, depending on individual cases. We take students with background and at the bachelor or master's level in computer science, exact science, and science of engineering. And this is more or less the structure of our program in a very schematic way. But basically, we have 4 mandatory courses. I mean, during the first term semester, the students have to take a course on stochastic and statistical techniques in data science. Also, topics in data management and analytics. We assume that they already know something about databases. I'm going to say a bit more about this in a minute. During the second semester, they take a mandatory course on linear algebra and optimization methods for data science, and a second course on machine learning methods in data science. These are the 4 mandatory courses, the core of the program. And in addition to that, they have to take 3 elective courses and a thesis seminar where they, at the end of that seminar, basically they propose the research that the students are going to carry out during the rest of the program, basically the next 3 years of the program that are basically concentrated on thesis work. Yeah? So of course, there might be some people who don't have the background, more practical hands-on background. So we offer an initial hands-on 2-week boot camp on Python programming and practical aspects of databases. That has been really successful. The students that take this bootcamp in the context of the Master of Science in Data Science, they're very happy about that. So we are planning to continue in that direction. This is very important. Some areas of research interest, I'm going to mention some of them that we represent, that we develop. We have data management, as I mentioned before, in the broad sense. Machine learning and data mining, natural language processing has become particularly relevant in these days. Knowledge representation, ontologies and knowledge graphs, uncertainty management in data and knowledge. Explainable AI, as I mentioned before, this is a very important area with many ramifications. People want to understand what's going on with these machines, these algorithms that produce results. I mean, they want to understand what's going on. I mean, when they see a result, right? If someone is applying for a loan at the bank, I mean, and receive a rejection or a negative result, I mean, the client wants to know, why am I being rejected, right? So the system that automatically classify people who are requesting loans, I mean, should be able to provide explanations. There are many ethical issues involved in this area, fairness, bias, etc., etc. So it's quite a hot area of research. Neurosymbolic AI, as I mentioned before, for the need, I mean, to combine different approaches. We have predictive and prescriptive analytics, statistical methods in data science and machine learning. We have a large group of statisticians in our group who are working in this direction. And of course, different applications like biostatistics, bioinformatics, statistical genetics, and so on. And quite crucially, in the last 2 years, I mean, we have been doing a lot, I mean, as a group, as a university and faculty around, I mean, astronomical, spatial, and satellite data. That is a very, very important. So basically, these are areas that we are representing. Of course, we are open to new areas, emerging areas or interest, but this is something that we are really doing and very much interested in. And what now, all I have to do is basically, invite you to join us, both as students and also as collaborators in different ways. I mean, so you can find, more information at this webpage. I mean, I can share the slides with you if you're interested, or you can, the most easy thing to do is just contact me or Natalia Peña, who is hosting this event, and we will be happy to provide information. So we want to have an impact. We want to reach to you and hopefully bring you to our program. You are very much welcome to join us again. Yeah. So this is what I wanted to present. We are a bit ahead of the schedule in the sense that our invited speaker was supposed to present at 2. I would like to know if he is around. I mean, otherwise, we will have to wait a bit. So Luc de Ret was still to present at 2. Maybe we were too fast in our introduction. I'm trying to check if he's around.
I'm around, so.
Oh, look, it's here. Okay, great. Yeah, that's wonderful. Okay, I think we can start. I'm going to introduce. Can you turn on your camera, perhaps, Luc? Nice to see. Oh, that's great. Okay. Well, as I said, I mean, I would like to introduce our invited speaker. Let me stop sharing the screen. Okay, we're fine. So I'm going to introduce our invited speaker, Luc de Ret, who is a professor of the Catholic University of Leuven in Belgium, and the director of the newly created the Leuven AI Center for AI Research. I am not going to read the impressive, bio we share with all of you. I prefer to say what immediately comes to my mind when I think of Luc de Ret. Yeah? Well, I had the luck to meet him in person at a small and by invitation only workshop on a statistical relational learning some years ago, around 7 years ago, at the Banff Research Center in the Canadian Rocky Mountains. I was basically an outsider in this area of AI, but very much interested in the area. But I felt immediately welcomed by him. He's a very nice, friendly, and approachable person, and always willing to help and collaborate. Of course, I had been and still am following his trajectory and research. He has made and is making important contributions to different areas of AI. By the way, I should mention that he is a fellow of the AAAI. That is an important recognition from the AI community. It's the Association for Advancement of Artificial Intelligence. It is also remarkable that he has created a school in the true sense. I mean, he has produced many important academic children who are now respected researchers across the world, and has contributed to making Leuven one of the poles of attraction for AI research. In the last few years, has been advocating for and doing pioneering work on neurosymbolic AI, which is crucial for the full development of artificial intelligence. But he will tell us about this. Many thanks, Luc, for agreeing to take part in the launching event of our PhD program in data science, and the Zoom is yours. Thanks a lot for being here.
Thanks a lot for the kind invitation. And first of all, let me congratulate you with your new doctoral school. I think data science is an exciting topic, and the list of topics that you mentioned is indeed having all the characteristics of successful research at an institute, going from statistics to applications to AI, machine learning, and from theory to practice. So I think there's really a lot of breadth in this topic. So I think it's the cool topic to be part of. So I'm very honored to be here and to give the first lecture, so to say. Let me try to share my screen. Okay, share the screen. That should work, hopefully. Can you see the screen now? Or?
Yeah, it looks fine. It looks fine. Yeah.
Okay, perfect. So what I want to do in the next 45 minutes or so is give an overview of the field of statistical relational AI and neurosymbolic computation. And these are like two subfields of AI that combine different paradigms. And I think combining different paradigms is also very essential in data science. And so this is joint work with a lot of people, a lot of my collaborators who are mentioned actually at the bottom of the slide. The motivation for this work is very much the thing that is probably on the top of the agenda in the field of AI. That's like really integrating learning and reasoning. And that quest for integrated learning and reasoning comes back in many different forms. First of all, there is the seminal work by Nobel Prize winner Daniel Kahneman, who has written this fabulous book on thinking fast and slow. And in cognitive science, they distinguish system 1 from system 2. System 1 is the kind of thinking fast. If we just look at the Zoom screen and we see all the faces, we directly recognize who is there. We don't have to think about that. That's the kind of thing you also do when you do computations like 2 + 2 is, you directly know it's 4. You don't really have to think about it. So it's going very fast. On the other hand, there is system 2, which is about reasoning and typically multi-step reasoning. You solve some complex problems, like if you plan a trip, you're going to several phases. Where are you going to go to? What means of transportation are you going to use? When are you going to start? So there's a lot of steps to do. Also, if you solve mathematical exercises, this is exactly what system in your brain you're using. And this distinction comes back in a lot of AI. If you look at the state of the art in neural networks, then it's very much the system 1 kind of thing. It produces something, but you don't have to think about it, but it also doesn't allow you to provide explanations and the like. On the other hand, if you look at things like reasoning, then that's typically the topic of system 2. And so the distinction is known as the data-driven versus the knowledge-driven approach, symbols versus sub-symbols. Hector Geffner likes to use solvers and learners. And everybody agrees that the key question is really to integrate these paradigms within AI, because they've been quite separated from another. And there are arguments from people like Jan LeCun, Benjo, but also from the other side, like Gary Marcus, Anand Darwish, Josh Tenenbaum. So from all different sides, people agree that this is the problem. What they don't agree on is how to do this. And that's where there's a lot of discussion today. You can also see that this is what you really need to achieve real AI. I mean, if we pass our driver's license, we have to answer this kind of questions because they're important if you're in traffic. And it's exactly this kind of ability that you would also expect from cars that drive themselves, that they would also have these abilities. Now, what does it take for an AI system to kind of answer this kind of question? Well, first of all, you need to recognize the entities in the scene, like where are the cars, where are the pedestrians, the traffic signs, and so on. And secondly, you also need to know the rules of traffic, the kind of traffic rules and law, in order to be able to decide about who can go first and whether you can continue to drive or whether you have to stop at the stopping sign. And so one part is really like the computer vision, the sub-symbolic perception. The other part is really the kind of reasoning. So ultimately, AI systems need both of them. If you look at the state of the art in AI, then the key paradigm for thinking fast is no doubt neural networks. There is a focus on learning, and it has achieved amazing results. Very cool and very applicable technology. But also what's sometimes forgotten today is that also in reasoning, there's been a lot of progress. And there's two main paradigms for reasoning that are typical for AI. There is on the one hand logic, and on the other hand probability and probabilistic graphical models. And the integration of these two paradigms is well studied by now. It's about 20 years or so that people talk about statistical relational AI and probabilistic logic programming, and they basically try to achieve this integration. The quest for integrated learning and reasoning is described by Pedro Domingos in his book, his best-selling book, The Master Algorithm, and he describes 5 schools of machine learning and AI, of which you see 3 here. There is 2 more, which is like evolutionary computation, and also like the reasoning by analogy, so to say. But like one quest is really to come up with the ultimate algorithm that combines as many of these paradigms as possible. And I'm going to focus on these 3. Today, people talk a lot about neurosymbolic computation, and that's like one of the areas that's viewed as the next wave in AI, basically. And what they do is combine logic with neural networks. And so there is one kind of key message that I have. I come from the field of statistical relational AI, which studied the integration of probability and logic. And I view, when I look at neurosymbolic, I see that there is a lot of commonalities between the 2 fields. There's basically a lot of techniques that Starry Eye and neurosymbolic share. And because they share so many problems, it also means that similar solutions do apply. And that's going to be what I'm going to try to argue in the first part of the talk. Maybe this doesn't cover all of neurosymbolic. There's people that focus on language, and that's not something that I will do here. If you look at the state of the art in neurosymbolic, then the vast majority of approaches, they use logic and they use rules or knowledge to represent this kind of declarative knowledge. And the way that they integrated the neurosymbolic computation is basically that they try to inject, to reduce the logic and push it inside the neural network, and then assume that the neural network will do the rest. But the downside is that this is a one-sided approach, and that the typical power of reasoning, like being able to provide explanations, to be trusted, and to do kind of real logical or probabilistic reasoning, that is to some extent lost. And that's why I want to give you also a flavor of what we do in Leuven in my group, where we take a different approach. The feeling that we have is that if you integrate 2 paradigms, say X and Y, and you obtain a true integration of these 2, well, then you should be able to reconstruct the originals as special cases, so to say. So if you're integrating neural networks and logical reasoning in a system, well, then you want that system to be able to do pure logical reasoning and pure neural networks as well. And that's not what most of the state of the art does. And that's what I'm going to try to illustrate that our approaches try to do. They try to do this by building an interface, so to say, between the logic and the neural networks. So my first part is going to be about mapping this statistical relational AI, these logics, probabilistic logics, and making the analogy to neurosymbolic. And I'm going to introduce a little bit of a flavor of the 2 different paradigms. So the first key message is really that they share similar problems. What you see if you investigate, if you look at the state of the art in these fields, then it turns out that there is both in neurosymbolic and in stare, like two basic types of systems that are being used. And that corresponds also to the kind of systems that you use in probabilistic graphical models. There is the directed and the undirected, and they come back in a sense in the logic, in the graphical models, and also in the neural networks. So let me start with the logic. Here is a simple logical knowledge base. It's purely propositional, and so what you see is that there are some facts that are true statements. It is the case that there is a burglary. It is the case that Mary hears the alarm, and so on. And then you also have the kind of rules, and here I use the prologue or the logic programming notation for that. That rule here says that Mary calls will be true if alarm is true and Mary has heard the alarm, basically. Then it's like an if-then rule that is pretty declarative and that you can use here. It's logic. So with logic, you can prove, and proving is what is done to answer queries. So here you can now build a proof. Does it follow from that knowledge, from that logical theory that Mary calls? And what you see on the right hand of the slide is two proofs for that. Basically, to show that Mary calls holds, what you do is you apply these rules for Mary calls, and you look at the condition part of that rule. And if you can prove that condition part, okay, then Mary calls will be true. And so you recurse on that principle, and ultimately you come up with two proofs for that, that query, so to say. And that's like one kind of view. You've got a directed model, and you do a kind of proof-based approach. The other view of logic is the view of logic that you find in constraints, in logic as satisfiability. I mean, SAT solvers are amongst the most useful tools and the most important problems in computer science. And so again, you see like a logical theory on the left, and what you're then looking for, given such a logical theory, do I find a possible world that satisfies all these constraints, all these logical statements? And for instance, you can see that this possible world where I say these are the facts that hold, and everything that's not in the set doesn't hold, that's supposed to be false. You can see that that possible world, that it satisfies the first rule, because indeed well, Mary calls is not occurring in there. So, well, then the rule is clearly satisfied. It also case that the other rules are satisfied here. And that's a bit the model theoretic perspective that will be important. Now that's logic, where you have these two views, the kind of proof theoretic and the model theoretic. Now, if you look at graphical models, you know, the probabilistic models like Bayesian networks, Markov random fields, and so on, you got very much the same kind of division. On the left, you see a Bayesian network, the standard network due to Judea Pro. On the right, you see Markov logic and a Markov network that's kind of an instance. And so we're now going to develop this kind of connection a little bit later. And it turns out that also with neurosymbolic systems, it's exactly the same kind of distinction that you have. On the one hand, you can use the logic to build, in a sense, your neural network and to reason. And that's like the left approach, the neural program, so to say. And on the other hand, you can use the logic to impose constraints on the neural network, to use the logic as a kind of regularizer. And that's very reminiscent of this Markov logic networks. So let's illustrate the ideas here. If you look at one of the earliest approaches to neurosymbolic computation, that is due to Jude Shavlik and Towel already in the 90s, the famous system known as K-BAN. And what they would do is like they would take a bunch of this prologue rules, this rules that I showed, like for the alarms example, and they would kind of rewrite that in order to get the kind of tree structure. And so what I wanted to derive here is like, does A, and say A is the alarm, does it hold? and then the others are like features. And so they would use these rules to turn that into the structure of a kind of tree structure, as you see here. And once they have the tree structure, they would turn that tree structure into a neural network. They would do that simply by, adding connections from the from so to say the leaves of that tree. They would add from the leaves of that tree, they would add further connections to the other layers, and they would add like connections. They would also add here and there these gray nodes which didn't occur yet, and which are like corresponding to like unobserved variables or hidden nodes. And then they would train this just as any other neural network, and they would get interesting results. Now, it turns out that this kind of principle is still very popular if you look at current neurosymbolic approaches. There is work by the Kuzelka group in Prague, which is doing exactly this. They would take, logic programs, and they would turn these logic programs into proofs, and the proofs would then be turned into a neural network, very much like what you have here. There's also a fabulous, really recommended neurosymbolic system called the Neural Team Improver that does something similar, but also adds some interesting components. Like here, you've got a knowledge base like that is listed on the top left, where you see Abe is the father of Omer. Omer is the parent of Bart. And you also have like the definition of grandfather of. X is going to be the grandfather of Y if X is the father of Z, and Z is a parent of Y. And with this, you can build kind of proofs. You can try to prove whether, Abe is the grandfather of Bart, and that will succeed here. But then the problem that they address is pretty interesting, because they work with kind of soft unification and soft rules, because the original knowledge base says it has to be the predicate grandfather of, but maybe, your user doesn't know grandfather of, but he knows grandpa of. And then they would use like embeddings from natural language to show, well, grandpa of and grandfather of, they close an embedding space, so we can match this and we can apply the same kind of rules. And this is very much the kind of same spirit as K-band, except that they added this fabulous soft unification, so to say. In both approaches, once they've constructed the proofs and turn it into a neural network, the logic disappears, and you can no longer apply the typical kind of logical reasoning or explanations that you would like to get. And that's one of the downsides. We can also look at the other side. Here is an interesting example due to Xu et al. From an ICML paper with Guy van den Broek. And what they do is they take normal neural networks, like the one on the left, where you do, for instance, a multi-class classification, and that means your output nodes give you a kind of number that indicates how much the neural network thinks this is class 1, class 2, and class 3. Now, what you see here is that if you want to predict exactly one class, then this is not a favorable situation, because the third and the first class have very high beliefs, so to say, and they're in a sense incompatible. It's not like a probability distribution. And so what he and his team have done is they impose constraints on the outputs of the neural network. Like if you do multi-class classification, you want exactly one of the output nodes to fire and not all three at the same time. And so what he does is you just provide this constraint, like in logic, exactly one of these three outputs should be true, the others should be false. And that's like the logical way of writing that. And then they use that to regularize the neural network. And they compute, in a sense, the probability using this 0.8, 0.3, 0.9 that this constraint is satisfied. and that's used in what is called the semantic loss. And if the neural network doesn't satisfy these constraints, it in a sense gets penalized. It gets regularized in a sense, and so it's pretty nice mathematically as well. But the intuition is very much that you impose constraints, and then that the degree of satisfaction of that constraints will tell you something about how good the network performs, and can also be used to train the neural network further. And again, that's like a second technique that comes back and back and back in neurosymbolic approaches. There is the logic tensor networks by Luciano Serafini and Arthur Garcet, which do something very, very similar. They've got a structure of their Bayesian network, and then they impose soft constraints on that they try to enforce, essentially. Semantic-based regularization from the group in Siena around Marco Gori and Diligenti is doing something pretty similar. And again, what you see is that once you've declare the logic and you use it to penalize or regularize your neural network, the logic disappears, and you don't longer use it anymore while you do inference in your neural network. And so that means that you have two types of neural symbolic systems. One is like really the kind of neural program. The other is kind of the logic as the regularizer. And that corresponds closely to this directed starry-eye approaches, the directed graphical models and the undirected graphical models. And so that's, confirms in a sense that alongst this one kind of most important dimension, starry-eye systems and neurosymbolic systems and PGM systems, probabilistic graphical models, are very, very similar in kind of nature. And another question that you can ask is, what do the numbers mean? And again, there is like 3 different choices that people make in neurosymbolic, and that also comes back in the statistical relational AI literature. First of all, there is a desire to keep everything as logical as possible. And for instance, the system from Ziwa Zhu's group in Nanjing is doing that. But the downside is that if you're trying to optimize weights and stuff like that, that the optimization becomes pretty hard, because in neural networks, it's common to use gradient descent and these methods. There's also probabilistic methods, which is something that we try to use. They're pretty elegant and very natural, like as what this semantic loss is showing, but it's somewhat more computationally expensive. And then there is a lot of work, I should say the vast majority of neurosymbolic methods uses fuzzy logics. And the reason is really that it's makes the optimization a lot easier than using the probabilistic stuff. But on the other hand, you get less intuition and less kind of logical reasoning. So people use fuzzy for computational reasons, not because the meaning or the semantics is so nice. Maybe let me very briefly try to give some intuitions as to this logic as constraints and these ways where the differences are. So if you look at this possible vowels and you use as logic and probabilistic models, then what the probabilistic logics will do is they will assign a probability value to every possible vowel in a sense. And that then allows you to reason about things in the vowel, to make predictions and things like that. And so the typically also the probability values, they're associated to like tuples and facts, and like for instance the probability of burglary. That's typically one of the things. There's also this view of logic as soft constraints. I mean, before I was seeing it as hard constraints, and in that case, things like Markov logic, they would assign a weight on every logical constraint. And the intuition then is the higher the weight, the more important and the more constraining the constraint will be. And so if the weight is infinite, then it becomes a logical constraint. If the weight is very low, it becomes less important. So things become less likely. They typically don't become impossible unless you set weights to like infinity. And what fuzzy logics do is they go a step further in a sense, because they have the same view. Like they would also associate these weights to some of these rules to indicate, kind of soft constraints. But then in addition, they would also assign membership functions to some of these facts, like what you see on the right. And then they would look at the rule like you see at the bottom, like this John calls. If John hears the alarm and the alarm goes off, and they would use these numbers in a sense to say the degree of satisfaction of such rule. And there's a lot of different choices and T-norms and stuff like that that you can choose there. It allows you to optimize and search and find weights much faster than in the probabilistic case. But there is a price to pay, and that is that some of the intuitions, they don't longer hold. I mean, if you're in logic and A implies B, and B implies C, then you can be certain that also A will imply C. But with the fuzzy logics, with some of the T-norms, that is no longer guaranteed. And so a lot of fuzzy logics are being used in this logic tensor networks, in this semantic-based regularization, in this lifted relational neural networks. They all kind of use it. And the reason is really that you get faster optimization. So what we try to do is to take a different approach. And the approach that we take is, rather than, try to reduce one approach to the other, I mean, like push down the logic into the neural network, we try to keep both the logic and the neural network as kind of separate entities, and we study a kind of interface between them. Now, I should stress that an interface is something pretty different than a pipeline. A lot of people say, you're using a pipeline, but no, pipelines, I think they are for plumbers, and pipelines are also like one directional. And here you really have exchange of information in the two directions, from the logic to the neural network, and back from the neural network to the kind of logic. And so our approach, which is called dproblog, is actually an extension of a probabilistic logic programming language called Problog with neural networks. And the advantages are that in this case, you've got a programming language that is on which this is built. Furthermore, it's a probabilistic programming language that allows you to reason about neural networks, and it has logic, probabilistic graphical models, and neural networks as kind of special cases. And so you retain this, in my view, important property that the originals are special cases. And you got a pretty nice semantics of that. I'm going to illustrate that in two different steps. First, I'm going to go from this little alarm example to like a probabilistic alarm example. And then I'm going to go to add the neural part. So let me briefly start with the first part. I mean, this was the kind of prologue program that I was showing. You have some facts and some rules, and you can build proofs with that. And that's purely logical. Things are true or false. And it was the contribution by, seminal contribution by David Poole and Taisuke Sato to realize that you can really turn that into probabilistic programming languages. And that's already in the early 90s that they realized that. So this idea of probabilistic programming has its origin in logic programming. Although a lot of people that are now working on probabilistic programming believe that this was invented like around 2005, but it's actually much, much older. It's Southland Pool that really did seminal work there. And the key insight that they had is, in order to unify logic and probability, look at the kind of basic concepts in both logic and in probability and unify them. And what's the basic concept in probability theory? It's the notion of a random variable. And the basic concept in propositional logic is just a propositional variable. And so what they did is, let's just unify that. Propositional logical variables, they become random variables and vice versa. And once they had that view, the only other thing that they needed to do is really to look at these prologue programs. And they then looked at the facts, which before we had burglary is true, or burglary was false. And now they say burglary is true with probability 10%. Mary hears the alarm with probability 30%. And in a sense, that's all you need to add to the language to get a probabilistic programming language and a pretty nice semantics that you can do for learning, reasoning, and a lot of interesting stuff. The idea is also, people will always ask about this one thing. If you're familiar with Bayesian networks, then it said, well, these probabilistic facts, they're independent. Yes, they are independent. And then people think, well, can you introduce independencies? And yes, there are independencies. There are dependencies, sorry. The dependencies, they are introduced by the rules in a sense that use these to reason. The idea is simple now. The proofs that we built before are now turned into probabilistic proofs. Like there is the proof for the, I can't point to the slide, but there is the alarm network. And so alarm will be true if there is a burglary or if there's an earthquake. There is two possible proofs for that. And the proof, the probability of one proof is simply the product of these probabilistic facts that you've used in that proof. So the probability of the left proof is 10%, that of the right proof is 5%. And then, of course, it's tempting to say, well, if I've got two proofs, one with probability 10%, the other with 5%, it's very tempting to say the probability of alarm is going to be 15%. But that's, of course, a mistake. And that is a mistake that causes a lot of difficulties, because we know from probability theory that if you've got the probability of a union or the probability of a disjunction, well, you don't only have to add the two probabilities, but you also have to subtract the intersection. And so the probability of alarm here is equal to the probability of burglary plus earthquake, but minus the intersection, which is burglary together with earthquake. And that leads to computationally hard problems and intractability. So most of the work in this is really on making inference fast. There's another explanation of the meaning of these programs, and that's like as a kind of generative process. You see a little variant of the language, and you see also this kind of generative process where at the root, that's an empty node, and then you're going to go through your rules. And so the first rule that you encounter is earthquake. Earthquake is true with probability 1. And so at the second node, you get like earthquake is in there with probability 1. And then there is this third rule, which says if there is an earthquake, there's going to be an alarm with probability 60%. And so you can go left, and in the left node, then you've got both alarm and earthquake being there. In the right node, you've got earthquake being there, but alarm is not there. And you see that the probabilities are like 60% to go left, 40 to go right. And you can then do this recursively. They've shown that the order in which you do this doesn't matter, but at the leaves of this tree, you're going to get these possible walls. And For instance, the leftmost possible vault is containing alarm, burglary, and earthquake. And that is one that has probability, the product of the facts that you used along there. And so that's like 0.8 times 0.5% times 0.6. And that's like the left orange node. If you then want to know how likely it is that alarm goes off, well, you look at all these leaves of the tree in which alarm is a number, and that's going to be all these 4 oranges, and you simply add up their probabilities. Of course, this is the semantics. There's no way that you can do this generative processes and that this is going to be efficient. There's other methods for doing that. That's a bit the semantics of this. You can easily show, people knowing probabilistic graphical models have certainly seen this example from Judea Poe. You can directly map these Bayesian networks onto these probabilistic programs, but you can do much, much more in these probabilistic programs. One of the things you can do is also these plates. Here you see a simple Bayesian network in plate notation. It's about students, courses, and grades that the students get on the courses. And so you've got these plates. There's one plate for course, there is one plate for student, and that simply means that that part of the network is repeated for as many students and courses that we have. And here you see, if I fill out, a couple of students and a couple of courses, this is the kind of Bayesian network that I can get. And you see that this would allow you to do all kinds of interesting reasoning. If I know the grades of 3-4 students on particular courses, then that's gonna tell me, it's gonna give me some information that I could use to infer the probability of a grade of another student, or maybe also of the difficulty of the courses. And so that's something you can do with these plate notations. With the probabilistic programs, you can do even more. First of all, you can encode the plate directly in this program. The thing that you have to do is that for every entry in the conditional probability table of such a graphical model, what you will do is you'll get one of these rules in there. That's a pretty direct mapping that you can get, and then you can add information about the students and so on. So for instance, the red rule is the case when the student is intelligent and the course is difficult, then you can define, well, the probability of getting an A is 30%, a B is 50%, and so on, basically. But you can do much, much more. You can really integrate that with ontologies, like you may have knowledge about what are excellent students when somebody is unsatisfactory and fails the whole program, that kind of stuff. You can easily declare it in logic, so to say. Inference, I'm not going to say much about it because that's the tricky business. But basically what you do is you start from a program like on the left, and there's one change that I made, and I introduced this logical variable X, and these 2 constants, Mary and John. And in the first step, I'm going to ground it out. That means I'm going to replace these variables by all my possible constants and entities. And I'm going to get this one. Then I'm going to prove, if I'm interested in having the probability that Mary calls, I'm going to build all these proofs. And I'm going to turn that in a formula like this. And that formula is then mapped onto this circuits. That's with techniques from knowledge compilation. And on these circuits, you can then efficiently compute the probability that Mary calls. There's a lot of work on these kind of circuits. At some point, OBDDs, which is one particular type of circuit, was the most cited publication in the whole field of computer science. And that's actually compiling logical formulas onto particular data structures that satisfy certain formulas. And that's a computationally hard problem. But once you have it, it's everything becomes fast, and you get rid of this disjoint sum problems. There's quite some applications that you can look at. My students have looked at building models of multiplayer real-time strategy games, where you basically have these game states. These game states contain, different entities like alliances, cities, players, and so on. And there's relationships, so it typically evolves over time, and it evolves rapidly. And the question then is, can you build models for these games? Because if you can build probabilistic models, you may be able to use this to predict what's gonna happen in the next couple of time steps. And if you're able to do that, you can take better action. We also have done applications in tracking and robotics. Like on the right, you see reasoning about occluded objects. We've done things with robotics and with real robots. This is the simulation that you see, where in the first step, you look at what are the effects if you do simple actions on a table configuration with simple objects. And that later on, you learn the effects of the actions. And then you can use that to do planning, for instance, to get the objects in a particular configuration on the shelf. And that research is still ongoing in my group in Sweden, actually. There's been applications in biology to reason about best explanations for certain molecular profiles in probabilistic networks. There's been a number of papers on that. If you want to try ProbLog out, go to this website. There's a nice tutorial. You can play with it. You can also enter your own programs, and there's a lot of tutorials that go with it. Last but not least, I would say, let me also give you a flavor of the neurosymbolic part. And that's the most recent extension that is very exciting for us. If you want to take this probabilistic logics and you want to add neural networks, then the question is, what is like the simplest way of doing that? And it's always a good idea to look at the simplest, non-trivial ways of doing something. And here we tried to make an analogy with what Sato and Poole did, like trying to unify logic and neural networks. And we saw, well, a neural network that's something, and that could correspond to a so-called neural predicate. And for instance, this neural network that classifies an MNIST image into one of these 10 classes, while it will compute a kind of probability of the different classes, and let's encapsulate that in a neural predicate. And that's like the interface that we provide between the two. And that's, in a sense, well, the essence of the integration. It's all that you need, and it's something that other people have also taken over, in a sense. This is then the kind of declarations that we have. I mean, MNIST-net is like the name of the neural network. X is going to be the input. The input is going to be one of these MNIST images, and you're going to produce an output Y that will map to one of the 10 different classes from 0 to 9. And once you fill out, once you call that neural network or that neural predicate with a certain MNIST image for this variable X, what it's going to do is it's going to compute these probabilities, and it's going to turn that into this kind of probabilistic logical statements that says, I believe that with 4% it's a 0, 35% it's a 1, and so on. And so that's pretty simple, but it's pretty powerful, because you can now use that to define very simple things, like the definition of addition, where you can give you can try to learn a kind of predicate or program called addition that takes two of these images and produces the sum of the two images. And the way it does that is by using this very same neural predicate called digits. So that's like the rule that you see here. X is first going to be mapped onto a number n1. Y, the second MNIST image, is going to be mapped onto n2. And then Z is just the sum of the two, basically. And you can learn that. You can learn this neural predicate digit without any training example at the level of digit. The training examples are the ones that you see on the top right. It's of the form two MNIST images and their sum. And the reason why this works is that, well, you can now ground out this program. If you fill out this 358, you basically get this, and you see that the program is actually enforcing a constraint to hold between the mappings of the first image n1 and the mappings of the second image n2. You know that the sum of the two must be equal to 8, and that gives it information. You know that 3, 5 are possible, 4, 4 are possible, but 5, 6 are impossible because their sum is 11. It's not equal to 8 in a sense. You can then show that this does better than classical neural networks that don't have this knowledge, and it would be very hard to use this knowledge in these neural networks. And people in neural networks may say, well, that's still something we could do. Of course, that's true. But things like what you see at the bottom, where you work like with these lists of MNIST images that you try to add, that would be pretty hard to do with regular neural networks. In this framework, it's quite easy to program. The thing that you do is you just encode the rules of addition in Prolog, and you get this kind of multi-addition. Again, this very same neural predicate that is mapped to a neural network. And then by training with examples at this top level, this digit is going to be trained, and you can show that this also works pretty well. About inference and learning, let me just say that the kind of circuits that you get that I talked about, that you can connect them to the neural networks, and you can do just gradient descent from the logic to these leaves of the circuit and then down into the neural network. So all the standard machinery of both these probabilistic logics and these neural networks say gradient descent, it just works as expected. And then you can do some experiments. We've done quite a number of them. You can use it to learn a kind of programs. For instance, you can learn how to sort numbers. You can do these additions. You can also solve some word algebra problems, like what is listed here. Maybe I show the program synthesis kind of flavor, where you give a kind of program with what we call a hole in it, kind of a sketch. This whole thing is basically, it's gonna accept two numbers, and then it's gonna say like which one is the larger of the two, and this whole is then mapped onto a neural predicate called swap. And basically swap is, well, it's x is larger than y, or it's smaller or equal. That is what this is actually learning. And we've compared that approach with other approaches, and it turns out to be a bit faster. You can also model noise. Like here is a noisy version of the addition, where if it's not noisy, you do as before. If it is noisy, you just generate a random number, and below you see what is being learned. You see also that depending on the noise, on the parameter, on the choice of the noise parameter with which you generate the data, that of course you're going to have different positives and negative examples. But here it turns out that you can actually recover the noise level by just using the traditional training that I have described. You can also play with settings like poker, where you try to predict probabilities, like for a particular hand, how likely it is that you're gonna lose with the information that is available, with the cards that are on the table. So that's the typical kind of reasoning about uncertainty. This is the neural tier improver, again, where you have this very cool matching between grandfather of and related words, like grandpa of, and you can simulate that in the problem by defining, so to say, this kind of notion of soft match or soft unification. That's all things that you can basically do. So you can map it, and then you can integrate that with some of these concepts, in a sense. Like in one of the experiments, we were trying to use a different type of, to learn a different type of predicate, like the predicate that you see here, where you've got two numbers and you look at like what's the difference and how many numbers are in between. And we try to also embed these in space, and then you get something like what is on this slide. The digit with 0 would be mapped, I guess, in the top right, and then so it really decreases, and so you see that it really learns to correct distances between the numbers. Left is the situation before training, right is after training. There's other data sets that we've tried. We're also developing a variant of the problem, which is more grammatical based. Like if you know about probabilistic grammars, it's very much in the spirit. And you can do examples of this form, basically, where again, you've got like these expressions, and you use a kind of probabilistic grammar that's also coupled to a neural network, and with neural predicates to learn sums to learn the results of this kind of expressions. That's the latest in the development here. So to summarize, I think I've talked for 50 minutes, so that should be that's correct, right? So the challenges are to scale up. While in the original version we only had this exact reasoning inference engine, we now also have like an A*-like algorithm that was just published at KR, and that is much faster in some cases than the standard deep problem algorithm. I guess scaling up is an issue for a lot of these neurosymbolic systems. Another challenge is to decide about which models to use when, and neural networks are pretty hard to master and hard to learn as well. And sometimes it's a bit of a black art how to make them work together with this neurosymbolics. But the idea is that if you have knowledge, you should be able to provide it to the system, and that should give inspiration for doing this. I want to stress that I think this is an excellent area for starting researchers, because it's really like one of the key questions in the field. Many people view neurosymbolic as the next wave in AI, and there's so many cool challenges from different angles that it's pretty interesting to look at. And there's lots of challenges in theory, logic, probability, neural networks, and so on. Let me summarize the key messages. I have tried to argue that logic, probability, and neural networks can be combined, and also that there's a lot of commonalities between, say, probabilistic logics, neural logics, and even logics and probabilistic models themselves. This kind of categorization in these two classes of systems is one of them. And then I've also given an approach that we developed in our lab, and that is viewed as a kind of interface layer, not a pipeline. So thanks a lot for listening.
Thanks a lot, Luc, for the excellent, fascinating presentation that you gave. I would like to offer the possibility of asking some questions, if there are any. If that is okay. So, if someone has a question, we can maybe we can give the permission to ask the question aloud directly, or you can always write it in on the chat, and I would read it. I mean, so either way works fine. Are there any questions? I do have a couple of questions, but I don't want to monopolize the the camera. Or...
May I ask a question?
Yeah, Alvaro. Nice.
Yeah, thanks, Leo. Thanks, Luc, for this very interesting talk. I have a question about the semantics. These tensions you always have on a logic program with the semantics of negations that, well, the logic programming community has been struggling for 30 years. So, well, negation as failure or closure assumption, or, well, you name it. I wonder whether this tension also is mirrored in the deep probe-log transformation or in that domain, whether there is a kind of issues there mapping from one to the other.
Right. So yeah, it comes back in the probabilistic logics, and yeah, the first semantics was just for definite clauses, so like ignoring the negation, and then there's been a few variants with negation in there. I must say that in Neurosymbolic, we're not that far yet. I think most people, well, most systems don't really have a good semantics, if I may say so. It's also what you see in some of the early work in probabilistic programming, where people were developing systems. And they did useful things, but 5 years down the road, they were organizing workshops on the semantics of probabilistic programming, and I expect something like this to happen for Neurosymbolic as well. Having said that, I'm quite pleased that you can give a semantical interpretation of deep problog. The neural predicates you can, in a sense, treat very closely to the kind of predicates you have in problog, and so a lot of the probability, the semantics is retained, but it doesn't cover the negation as yet. But yeah, also, so that semantics is not as easy, because like one of the difficulties is, like, if you look at these images. I mean, if you fix the images, then it's kind of, you get the normal, you can view them as constants, so to say, and then you get like the normal Herbrand semantics with probabilistic interpretations of that, so like the distribution semantics. But yeah, if you want to leave that open, and in a sense, one of the cool things with neural networks is that you can generate new images, and what's the semantics of that? And so it's like, yeah, there's different interpretations there, and also there are kind of tricky questions that, well, I think we just scratched the surface of that. But I guess we're one of the only ones that claim to have a real semantics. I mean, there's some people that also have the fuzzy semantics, but with the fuzzy semantics, of course, technically speaking, it is a semantics, but it's chosen for, yeah, computational reasons. It's not chosen because of the logic and the understandability in many cases. It's not to deal with uncertainty in the sense of fuzzy. It's like also there is a lot of things to do still, but most people are right now building systems, and that's a bit what we've also seen with this probabilistic programs and probabilistic logics at the start. It was 20 years ago, it was very fashionable to build new systems and then say, well, my system can do everything your system can do, and I can do a bit more. I mean, this is like what everybody was claiming. There was even a name for that. It was like the alphabet soup of systems. I think today we've got the alphabet soup of neurosymbolic matters. It's also interesting to see that today in Starry Eye, few people still talk about expressivity. My system can do more than yours. I mean, this is not something that's kind of fashionable to say. People focus on the problems, and it's this, and these races go fast, right? Neurosymbolic is going extremely fast. There's so many people jumping on it, and it's going very fast. So yeah.
Thank you.
Yeah, thanks a lot. Well, I have a question. If you have questions, you can raise your hand, but of course. The immediate question is: so as with Problog, do you have a system which one can play with? I mean, an implementation.
Yes. Yeah, so with Problog you can play. It's just on the web. There is a nice interface where you can type in programs and play. Also, the Problog is available. You can download it. I think it's it's usable, but it doesn't have like the nice tutorials and online interfaces as Problog itself. And also, so some people have downloaded it and are playing with it. So you can also use that one. And we're very welcome. You're very welcome to send us questions. We're always interested in improving it. So
that's great. I have a more technical question. Well, at some point you were somehow mentioning the need for explanations. I mean, how does this combination that you're proposing, I mean, work in that direction of providing explanations, considering that you have these two elements, right? At some point you have to access the neural network. I mean, so I don't know, have you tried to do something in that direction as well?
Well, yeah, there you get some things for free, and I think we haven't put that, we haven't emphasized that enough, because again, if you look at the probabilistic logics, then there is the view of David Poole, like 30 years ago now, was that it was probabilistic abduction. And so it was giving explanations. You can give like a most likely explanation. And so, for instance, one explanation for the addition example that you could give, like a normal neural network would just say, well, it's 5 to sum, or it's 7. But here you could say it's 7 because the first digit is interpreted as a 2 and the second is interpreted as a 5, which is already kind of a form of explanation that you can do something with. Of course, going inside the neural networks, that's still a lot harder, and that's something we haven't done yet. But we're looking into explanations and this kind of stuff right now, actually. So yeah.
Okay, but the approach will be basically through abduction. At least I understood correctly, right?
Yes. Okay. A bit like in databases like lineage and that does apply, I think. Yeah.
Okay. Are there any questions? I mean, I still have one more question I would like to ask. I mean, take advantage of the opportunity. I mean, in page, I think it was 48, you mentioned the work by Venekens and colleagues, I mean, on causal.
Yes.
I mean, in the recent, during this last year, I would say, or maybe the last 2 years, I mean, people like Benjo and Sholkopf, they have been pushing forward the idea of using causality as opposed to pure correlations of probability in learning. So I wonder if you could somehow take advantage of these causal programs that you mentioned, I mean, in order to somehow bring causality into the picture as well. I mean, it's a very, I know it's a fuzzy question, but yes, yeah, think aloud.
Yes. This is a good question. I think there are some possibilities there. We're starting to look a little bit into that, but we don't have any kind of results yet. But I think it should be possible to do some stuff there. But I think it's quite different from what the neural network people do. They look at it way more statistical, and there's of course also the views by Judy April that are quite interesting and exciting. And so I think, probabilistic logics are probably much more suited for the kind of counterfactuals and this kind of stuff. So because they're close to graphical models. But that's an interesting idea, and I'm telling my student who's starting to look into that this would be something really, really cool to have.
I agree.
Kind of neural logic system that would provide explanations, and some of the other stuff that the causality, and that would be really, really cool.
Yeah, well, we'll be happy to collaborate if there is opportunity. Okay. We're very much interested in the area. Okay. Well, I have many questions, but at some point we have to stop. So I will be happy if there are any questions for the audience. I mean, it will be, I don't know. Otherwise, we are going to start converging to the end. And I give the word to Natalia as our host. And Luc, thanks a lot, I mean, for your presentation, for accepting our invitation. It's been really important presentation and really enjoyable presentation. And so it's great. Thanks a lot. I don't know if you could, most likely we will start receiving message about, can we get the slides from?
Sure,
you send me a version. I don't know if the same one that you're presenting. But
yes.
Yeah, it would be great if you can send them to me.
Okay, good.
We will post your presentation on YouTube, if I understand correctly, Natalia, if that's okay with you.
Sure, yeah.
Okay, great. Thanks a lot, Luc.
Okay. A lot of success with the school. So, yeah.
Okay. Thanks a lot, Luc, again. Natalia, yours.
Gracias, Leopoldo. Luc, thank you very much for your presentation. Damos así por terminada esta ceremonia. Agradecemos a todos quienes nos acompañaron esta tarde y los invitamos a conocer más acerca de nuestro programa a través del sitio web de la Universidad Adolfo Ibáñez. Buenas tardes.